Okay, this is the solution to the SAC. Let's start with question 1 of the multiple choice section. Which important feature of a secondary cell distinguishes it from other cell types? Now, I thought this was an easy question. To be fair, I think it was done fairly well. We are focusing on the feature that distinguishes secondary cell from other cell types. In other words, we are looking at something that is unique about secondary cells. So if you look at the first one, a continuous supply of reactants are fed into the cell so that it operates without the need to interrupt the chemical reactions to regenerate depleted reactants. Now, this is a fuel cell, not a secondary cell. Hopefully you remember that. So the answer is definitely not A. B, you have a limited amount of reactants. So once these are depleted, the chemical reactions and electricity production cease. This is a primary cell. Okay, so it's not B either. Part C, the products of the cell reaction remain in contact with the electrodes so that once the reactants are used up, it is possible for more reactants to be regenerated. Definitely, this is C. This is the unique feature of a secondary cell that allows it to be recharged. Okay, part D, spontaneous redox reactions occur which allow movement of electrons to produce an electric current. Now, this is a universal feature for any battery, so it's definitely not something that distinguishes secondary cells from other cell types. Okay, so hopefully question 1 was easy for most of you, if not all of you. Moving on to question 2. The lead acid accumulator converts chemical energy into electrical energy via this half equation. So when you have this, which is a rechargeable secondary cell, you need to make sure you understand and actually can find the piece of information in the question which indicates whether the equations provided are for discharge or for recharge. So in this case, these equations, these half equations, are for the conversion of chemical energy into electrical energy. Now that is going to be discharge. Okay, so during discharge, this is your anode, and this is, you are at a point when you need to be able to recognize whether a half equation is oxidation or reduction, and to recognize whether the oxidation is occurring at the anode or the cathode. So this is the anode, electrons are lost, which is oxidation. And this is going to be the cathode, electrons again, so it is reduction. Okay. And then we need to look at what happened during recharge. Now I am going to also put the polarities of the electrodes here. So it's negative for the anode and positive for the cathode because we're talking about discharge here. When the cell recharges, we are looking at the back direction. So both reactions will be reversed. Now I'm just going to change the color just to show. Okay, that is very dramatic and it should not need to be that dramatic, but that's okay. So the back direction is recharge. When the lead acid accumulator is recharged, the first one, lead is produced at the negative electrode. Now that's correct. The negative electrode of discharge is still negative during recharge, but the reaction that happens now is reduction and it becomes a cathode. But lead is indeed produced. Now we are going to continue reading just to make sure we didn't miss anything. pH increases. Now that is wrong because as you recharge, you're going to produce, if you produce H plus ions, that is going to decrease pH, not increases it. So it's not B. Lead sulfate is produced at the positive electrode. Okay, lead sulfate is not produced at all. In both cases, it is the reactant. And the changes in oxidation numbers of lead are from 0 to 2 and 4 to 2. Now, this is probably not that necessary, but if you're really paranoid, and I tend to be when I do exams, I will go through every single option. So, okay, 0 to 2 and 4 to 2 is actually what happened during discharge, not recharge. So definitely the answer is A. So that's question 2. Okay, moving on to question 3. All right, this question. Now, this question in hindsight is a little bit too difficult. But I did try. It's very hard to, or maybe it wasn't. Maybe I should have just done that. I thought it would be too obvious if I give you any more hint. But with this question, all right, let's just explain it. Now, I did give everyone a mark because I thought it was too difficult. I think I tried to give you a hint, probably not too much, not enough of a hint. I don't even know what I'm saying. Okay, let's talk about what I meant. You have a solution of potassium sulfate, and it is electrolyzed using inert electrodes. The following half equations are provided in addition to the information. Now that's terrible English here. The following half equations are provided in addition to the information provided in the data booklet. Okay, probably could have changed the wording a little bit. But you have these two equations, and you need to consider what happened. What is the role of the sulfate ions in this case? Now, the key here is, well, this is basically a straightforward determine the products of electrolysis. So we're going to list every species present. So we have K plus, SO4, 2 minus, and H2O. And I think the key here is to recognize that H plus is not present, at least not in a significant amount. I mean, you can argue that some water self-ionizes into H plus and OH minus ions, but the amount is not going to be enough for it to participate in this equation. So even though two equations are provided for SO4 2 minus, you can't actually use the second one. So H plus is not present. And I know I gave it to you even though you can't use it because, you know, I'm trying to, I don't know what I'm trying to do. Okay, I know what I'm trying to do. I want to see whether you notice that. Anyway, and no one did, so there's that. We're gonna go to the periodic table, sorry, the electrochemical series, just to check. By this point, I really should have remembered this, but anyway, that's fine. So if we highlighted the species present, you have water. So let's just write, we have O2. I'm just gonna write the species, and this is positive 1.23. You have that present, and you also have H2O and OH minus and H2 at negative 0.83 volt. And lastly, you have K plus and K at, I don't know, something very, very, very low. Negative 200. Okay, that's not 200. Negative 2.93 volt. Okay, and we have that. So highlight everything that we have. So at the anode, we're going to have this turning into O2 and H plus, and here we're going to have that turning into OH minus and H2. So water is water is both the oxidizing and reducing agent, and SO42 minus ions is neither oxidized or reduced. The question is it going to be C or D? It is actually going to be attracted to the anode. I mean, if you remember, cations will migrate to cathode, and anions will migrate to the anode. In this case, because you have both cations and anions, and there's no indication of any limitations on how the ions can move, you can assume that the cations will migrate to the cathode and the anions will be attracted to the anode. So the correct answer is D. The SO42 minus ions is attracted to the anode where they are neither reduced nor oxidized. Difficult question. Moving on to 4. Okay, we did not need that space. All right, I can edit that later. An electric current is passed through a highly concentrated solution of potassium chloride, the reaction that will occur at the anode. Now, this is the exception that you need to remember. This is when you have Cl minus, K plus, and H2O present, and you need to remember that when the concentration of Cl minus is high, so if we have a higher, well, not higher, just high. Let's try that again. If you have a high concentration, then it can potentially outcompete H2O. So in this particular instance, the reaction at the anode is going to be oxidation of chloride ions going to chlorine gas and electrons. So Cl minus will be oxidized. I don't actually know why I need to write this. But anyway, instead of H2O. Oh, that was a mistake, wasn't it? Should have done this first. Now it's all going to be... Oh, no, it works out well. Alright, I'm just going to do this just in case. Alright, question 5. Easy question. I think people did fairly well. People really like Faraday's law. A non-rechargeable alkaline cell has a zinc anode with a mass of 1.2 grams. So the mass of zinc is 1.2 grams, assuming all of the zinc is oxidized to zinc 2 plus ion. So you need to get into the habit of writing the half equation down. You know that zinc is oxidized to zinc 2 plus, so zinc must be the reactant and zinc 2 plus must be the product, plus 2 electrons. If you write the half equation, you can be sure that you don't miss any mole ratio. Question asks, how long will the battery last? So we're looking for time. Assuming a current of 50 milliamps, so I is 50 mA, which you need to convert to current of amps, so 50 times 10 to the negative 3 amps. Okay, if I'm looking for time and I have the current, I need to get the charge divided by the current. So basically what you need is to find the charge. We're going to have to find the charge via the number of mole of electrons, which we can get from the number of mole of zinc. So step 1 is to find N of zinc, which is going to be mass of zinc over its molar mass. So we have 1.2, and I do not remember what zinc is. Let's see, 65.4. Okay, that was a correct guess. So 0.0183 mole. Now, mole ratio between zinc and electrons, according to the half equation there, is a 2-to-1 ratio. So the number of mole of electron is twice the number of mole of zinc, which means that I just need to double this number, which should be 0.0336697. I'm just copying as much digits as possible. You obviously should keep this in your calculator. So now we're going to find Q, which is N of electrons multiplied with, I forget, Avogadro's. Faraday's constant. I was thinking of the year 11 just then. So we would have 3,541.28 coulombs, and that's it. Lastly, time is Q divided by I. Make sure you convert it to amps before you do so. Okay, so I get 70,825 second. So we're going to divide by 60 to get to minutes, and then divide by 60 to get to hour, and it's closest to 20 hours. You definitely need more than 19.6 hours to account for energy lost. So that would be question 5, and I think I'm going to stop the video here.